Hello guys, today we are going to discuss about the minority electron and hole concentration in forward biased condition. What do you mean by this? Actually, we are going to apply forward bias or apply a voltage, okay, to the PN junction, and then we will see what will happen to the electron concentration when the PN junction is forward biased in terms of thermal equilibrium minority carrier concentration. So basically I will just tell you, suppose we have a PN junction, the bulk PN junction I showed you. So this is the metallurgical junction we got, the abrupt boundaries as we have already done. So this is P region, this is N region. In the N region, the abrupt boundary is Xn, and in the P region, the abrupt boundary we consider to be minus Xp. So this is the space charge region. In the N region, you got the positive space charge region, plus plus here, and minus negative space charge region. So here we said the electric field is induced here, the electric field is created here in the space charge region, right? So this is the electric field that is created in the space charge region. You can see directed from positive to negative. Now if you will just make it forward bias. Forward bias means what? This terminal is connected to the positive end of the battery or the cell, and the other terminal is connected to the negative. So N is connected to negative and P is connected to positive terminal of this. So this voltage, suppose I will say VA is the applied voltage. So now what you will see, the applied voltage here, you can see positive to negative. So this will be the direction of the applied voltage. I'm just writing it as EF. So this is the applied voltage. You can see the applied voltage is opposite to the electric field that is induced in the space charge region, right? So this induced space charge region actually prevents further flow of majority electrons from N to P and majority holes from P to N and maintains the equilibrium, right? This is what we have already done. So now when you apply this electric field opposite to the induced electric field, the diffusion force of the electrons, okay, from the N side and the holes from the P side will increase. So gradually this electric field which is induced in the space charge region will be affected, right? So and more number of charge carriers, majority charge carriers from N region to P region and P region to N region will flow, right? And ultimately the PN junction will have a current, right? So this is what we said. And if you remember the energy band diagram we had already done. So there will be, if I'm giving a forward biased, okay, applied voltage this way, then we said that the bending will be small, right? Okay, the space charge width will decrease. This is the conduction band in the P region, and N region, this is the conduction band we said. Now the Fermi energy level will be disturbed. It won't be constant throughout the entire system. So here we said the Fermi energy level will go little close to the the Fermi energy level, further closer to the further closer to the conduction band. The Fermi energy level will move closer to the move closer to the conduction band right here, because you connected this N type material to the negative side. So the average energy of the electrons will be more. The same way here, the positive or the holes are, or the P region is connected to the positive terminal. So the Fermi energy level of the P side will move closer to the valence band, right? So this is what we said, right? This is what we said. This is the bending of the valence band here. This is EV, okay, and EV in the P side, right? So now this gap we said is nothing but, here you can see the gap, okay. This gap is nothing but what? The amount of energy that you gave. So in terms of potential, you said VA is the amount of potential. In terms of energy, I can say this is EVA, right? This value is EVA. So here you can see this is the bending now. Earlier when the PN junction diode was in thermal equilibrium, the built-in potential barrier. Okay, we said the value was VBI. So in terms of energy gap or the bending is E times VVI. So now it is moving up, you can see. Okay, so the difference here, it is covered by EVA. So the, the gap over here, okay, this gap, okay, this bending, amount of bending, you can say, actually this amount of bending will be little less, pairs charge width will be less. So what is this value? Now earlier it was EVBI, so we can write it was VBI minus VA. The change in the potential now is this VBI minus VA. So the energy gap, you can see, or the energy bending here, bending of the conduction band or the valence band, or the intrinsic Fermi energy level, you can see the intrinsic Fermi energy level, which is actually, also bending by exactly the same way as that of the conduction band and valence band, right? So this was the intrinsic Fermi energy level, if you write EFI, right? Okay, so now we got the energy, difference in energy, which is EVBI minus VA. This is what we need. Okay, so now what we got, whenever we are giving a forward biased voltage, okay, electrons here in the n region will gain more energy and the diffusion force will be more. So more number of majority carrier electron will move from n region to p region. Similarly, more number of holes will move from p region to n region, and the p-n junction will will have current, right, through it. Okay, so now what we are going to do is, earlier, if you remember, we established a relation between what, the minority electron concentration here, minority carrier electron concentration in p region in thermal equilibrium, okay, in terms of majority charge carrier electron concentration in n region in thermal equilibrium. And it was found to be this. Refer to my previous video, we have already discussed this. EVI, VVI divided by KT. This is the equation that we did, right? Now, here in this case, what I'm going to do is, okay, when you are giving a forward bias voltage, the PN junction is not in thermal equilibrium now, right? Not in thermal equilibrium, but Fermi energy level is shifting now, right? So we said the Fermi energy level here, you can see, is moving close to the conduction band in the n region, and here it is moving close to the, the sorry, here, moving close to the valence band, right? So there is a, you can see there is a gap of EVA. So no more this is in thermal equilibrium. So the thermal equilibrium of the PN junction is now disrupted, right? Is disturbed, right? So now if I will write what is the electron concentration in the P region, zero I will not write, because zero was written for thermal equilibrium. Then what I will write, this can be written as n0, as it is. This is the majority carrier electron concentration in the n region, 0. And what is the changed value? The value actually, np0 became np0 to np because of the change in the potential barrier, and that change in the potential barrier is because of the applied voltage VA, forward bias voltage VA. So if I will write that minus E, and then in place of VBI we will write VBI minus VA, that is the value. Okay, so divided by KT, right? So that we can just expand it like, n0 exponential of the first term minus EVBI divided by KT, and then the other term, if you will see, e to the power or exponential of minus E into minus VA, that is plus. So we got EVA by KT, right? So let us use the first equation that we wrote, np0 equals to nn0 exponential of minus EVBI by KT. This is what we got over here, right? So this whole thing can be substituted for this np0 and can be written as np0. So let us write np0. Np0 is what? The minority electron concentration in the p region in thermal equilibrium, multiplied with what? Exponential of the rest of the term, EVA by KT. Okay, so this is what we got. So we got np is equal to this. Okay, so we got np is equal to np0 e to the power EVA by KT. So what is NP? N means electron concentration. It is minority charge carrier in the P region. So in the p region, so there is no zero here. That means non-equilibrium, because you applied a voltage to it, forward biased condition we said, so it is non-equilibrium. So this can be determined, okay, by what? By just multiplying the minority electron concentration in the p region in thermal equilibrium with what? The exponential of EVA by kT. So what amount of applied voltage is given? If this is known, right, and the thermal equilibrium minority carrier concentration in the p region is known, then you can find out at that particular value of applied voltage what will be the exact concentration of minority carrier electron in the p region. So this is what is the relation we are talking about. The same way you can do it for the whole concentration in the n region. So let me just write that. So we can also use the same way we can write, and we can write it as Pn as Pn0 exponential of EVA by kT. So these two equations we obtained, and the other one we got Np is equal to Np0 exponential of EVA by kT. So as we said, all these parameters, K Boltzmann constant, T is the temperature, E is electronic charge, Va is the applied mass, right? So let me just write what is Np. Np, N is minority, so I will write minority electron concentration in P region, because P you can see in P region in forward biased condition, right? So because it is not in equilibrium, if I write 0, then it is in equilibrium. And similarly Pn, you can write this is what? Minority whole concentration in the n region in forward biased condition, right? And what is Pn0? Pn0 is similarly minority whole concentration in a region in what? Thermal equilibrium condition. So this is what? Minority carrier. We said this is minority carrier whole concentration, okay, in n region in thermal equilibrium, okay. And similarly this one Np0, if you are writing, then you will write this is this as minority carrier electron concentration. N stands for electron, so electron concentration in P region. You can see P here in P region, that's why we said minority means it's in the opposite. Is it P region in thermal equilibrium? 0 for thermal equilibrium, in thermal equilibrium, okay. So this way we can actually, establish the relation between what? The non-equilibrium minority carrier concentration, okay, how it depends on what? The equilibrium minority carrier concentration when a forward bias voltage Va is given, okay. So this is the objective of our video today. So we established the relation between the minority carrier concentration in non-equilibrium to that of the minority carrier concentration in thermal equilibrium, right? So now if you will just show it in the space charge width, like in the depletion region, in the space charge region, how it will look, okay. So we can just, as I showed you in the bulk material here, we can draw the same thing. You can see xn is the abrupt boundary here, minus xp is the abrupt boundary in the p region, okay. And the metallurgical junction here, x is equal to 0. So the same thing I'm going to draw. So this is x is equal to 0, which is the metallurgical junction. The abrupt boundary, suppose, is this, which is plus xn, right? The other abrupt boundary somewhere here you take, so suppose this is x is equal to minus xp, right? This is x is equal to plus xn, right? And here we need to find out the electron and hole concentration. So what I will write here, suppose this is the concentration of hole in the n region, because this is our p region, okay, and this is our n region. So here if I will write what is the minority carrier hole concentration in the n region at x is equal to xn, okay. If you want to write this, I will write it as what, pn0, just now we derived, you can see it. So what we got, pn0 exponential eva by kt. So pn0 e to the power or exponential of eva by kt, right? This is what we got, right? Then so forward bias is given, so electron injection is happening in this way, in this direction. So electron injection means the flow of the majority charge carrier electrons in this direction, okay. Similarly, at x is equal to minus xp, if you will see, at x is equal to minus xp, some different concentration here, some other value you can say, okay, because they may not be equal your, okay, let me just write this value. So np means what, the majority here the minority carrier electron concentration in the p region at x is equal to minus xp, okay, at this abrupt boundary can be written as np0, okay, which is the minority carrier electron concentration in the p region in thermal equilibrium, multiplied with what, e to the power this eva by kt, eva by kt, right? This is what we got, okay. This is the value, this is the value here. Well, so and hole injection of hole is along this direction, injection diffusion force in the direction of, sorry, in the direction of diffusion force. So hole injection will be in this direction, right? Okay, so these concentrations I have shown you two different points, not exactly equal point. You can see somewhere here I drew this one and this one, because you can see the factor exponential of EVA by KT over here is same in both the cases, but you got NP0 here, NP0, which is electron concentration in the P region, and this is hole concentration in the n region. So this pn0 and np0, they are different. So we just put two different, two different height just to show the concentration are different, okay. You can say that this np0 is greater here, and pn0 is less, that also is fine, okay. So it is a variable, it depends, like what is the value of pn0 and np0. This is just to show you that this is how the distribution or the concentration can be shown at x is equal to xn or at x is equal to minus xp, right? So when there was initially pn0 amount of your holes in the n region, but when you applied a forward biased condition, when you give a forward biased condition, then what will happen, there will be change in the concentration of hole, okay, concentration of hole in the n region, because more number of holes will be injected. So definitely what will happen, the concentration of holes in the n region will increase. The same thing can be considered for electron injection. So when n region is connected to the negative terminal, electron energy will increase and more number diffusion force will increase, so more number of electron will be injected from the n region to the p region. So whatever your thermal equilibrium value was there earlier, right, np0, that will be further multiplied with what, exponential of VA by KT. So you can see, actually if you see, it's a exponential function for of VA, you can see. So the value of these minority carrier concentration in the opposite regions will actually increase exponentially, okay. So suppose I just wanted to show you some values, some random values here. Suppose this was the value and it was constant throughout, okay. So suppose this was your Pn0 earlier in thermal equilibrium and it was constant. Now you got this to be Pn0 multiplied with this exponential function. So somewhere here it is maximum, right? Okay, same way here. Suppose you will say that your np0 value was constant throughout, this was np0. Now this value is multiplied with this exponential function e to the power eva by kt. So you got this as maximum over here, right? So this is what we got from this video. Now in the next video we are going to see the minority carrier distribution. So we discussed about the minority carriers in the opposite region. That means electrons are injected from N to P region. So in the P region, these electrons are considered to be the minority carriers. The same way, holes were injected from P region to N region. Now these holes will be considered as the minority carriers in the N region, right? And we got the relation, like how they actually, depends upon the applied forward bias voltage, right? Then in the next video, we are going to discuss how these minority carriers will be actually distributed. Okay, so this is what we are going to discuss in the next class. Thank you for watching. Stay tuned.